Niche. Okay. Ko te wahanga tua whā, climate economics. We have three speakers. We've just tweaked the lineup slightly. We're going to open with Greg Boddicka, South African by birth, New Zealander by choice. And without any further delays, I'll hand over to Greg. And I'll say, I don't know if I'll really shepherd the other speakers through. I think I'm going to MC like I parent, with benign neglect. Okay.
I'll find a way to make it work. Kia ora, tēnā koutou, tēnā koutou, tēnā koutou katoa. Thank you very much to the organisers for inviting me to come and talk to you this morning. Look, normally when I just need to make sure that doesn't slide off. Normally when you invite a climate scientist to come and stand in front of a bunch of people and talk about climate futures, it's all about doom and gloom. And this will not be my talk today. Today I want to talk about some of the opportunities that arise because of climate change. Let's see if this is going to work. So I want to start off. No, I'm not seeing what. I see things on this screen, but I don't see them on that screen.
What happens when you... Yeah, you're right now.
There we go. Okay, good. Let's just make sure that's going to work. Good. Okay, so I want to start off by talking a little bit about climate modeling. Now, first of all, just to make sure we're all on the same page when it comes to climate modeling. The way we run climate models, I'm a climate scientist, is you divide the atmosphere of the world into lots of little cubes. You do the same with the ocean. And in each of those cubes, you solve the equations of physics, continuity and mass conservation and energy conservation. And you run the model forward in time, little time steps, maybe of 10 minutes. You might start your model in 1960 and run it through to 2100 under some greenhouse gas emission scenario, and you'll simulate the climate system over that 140 years. It'll typically take you about a month on a very fast, powerful supercomputer, and will cost you about $100,000 to do one model run. Now, why do climate scientists do model runs in the first place? So I'm going to tell you something. It's going to hurt a little bit, so brace yourselves. Climate modelers do not love you. They do climate models for completely different reasons to what you might think. If you are doing some biological research and you want to test something, you go and you buy 100 white lab mice, and you give them 50 of them the thing you want to test and 50 of them the placebo, and you see what happens. Earth scientists don't have 50 or 100 planets to do that on. So we create a computer model of the climate system, and we do experiments on those computer models. And all of the research that goes on is all about doing experiments, just making sure that you're seeing what I'm seeing, is experiments with these climate models. And so what tends to happen if you look over on the left of what you're looking at here, climate modelers are running climate models at maybe 100 kilometer resolution, so those little cubes that the atmosphere is divided into are about 100 kilometers by 100 kilometers. Think about what that means. That means that there's no differentiation between what the climate change in Invercargill is going to be to the 100 kilometers around. And we know that the climate changes a lot, especially over the Southern Alps, for example. You might run regional climate models at 20 kilometer resolution, but it's still a 20 kilometer resolution. You're only getting one number in every one of those 20 by 20 kilometer boxes. And then there's all the observations and data sets that go into it. Then, of course, every few years, the IPCC comes along, the Intergovernmental Panel on Climate Change, and says, look, we need some projections for how the climate is going to change out to 2100. Climate modeling groups find that annoying. They've been doing all this cool science, and now they've got to go and do these climate projections for the IPCC, but they go and do them under these different representative concentration pathway scenarios, different greenhouse gas emission scenarios, or these shared socioeconomic pathway scenarios. And they take all of that model output and they go and dump it into a big global database called the Earth System Grid Federation. It's about 2 petabytes of data sitting there. And if any business or finance group or anyone wanting to understand climate impacts goes to the global climate modeling community and says, where do I find this information? They say, no problem at all. It's all there on the Earth System Grid Federation. 2 petabytes of data. You can just go and download it and analyze it, and you'll be able to answer all of your questions. And that's as far as the climate modeling community goes in serving the needs of business and finance. And it's terrible. It's a horrible situation. What we need is Well, the one thing I should say is when you go and have a look at these pictures, down on your, I guess it's on the right, and look at what is needed to understand the impacts of climate change financially or economically. We need climate model runs at 1 kilometer resolution. We need to know at very high spatial granularity what's going on, where flooding is going to occur and where it's not going to occur. And to do that, you need to run climate models at 1 kilometer resolution. That's incredibly expensive, and I'll come back to that later. For financial regulation, you might need, okay, 100 kilometer might be enough. But for insurance, again, to know where flooding or landslips or those sorts of climate impacts are going to occur, you need very high resolution model runs. And the climate modeling community has been blind and deaf to those requirements for a very long time because they have been doing climate model runs for different reasons, for research reasons. The way it should be is like this, where you start with the needs of business and finance, and that defines what sort of climate modeling needs to happen. You need to have a climate services community. There's lots of opportunity there for business and economic development. There's operational prediction, where just like weather services run weather predictions, climate services need to run climate predictions so that you're not sort of beholden to the capricious nature of the IPCC or climate modeling communities who every few years go and do those climate projections. It needs to be far more operationalized. There's some challenges that come with that. One of them is that there's this disconnect between business demands and what science can currently provide. Science cannot currently provide what is needed. What does that mean? That means that there's opportunities to get cool stuff done, and I'll talk about that soon. Climate models are not designed to provide financially meaningful or useful information. Something like the annual average daily maximum temperature. That's something that climate modelers are always generating. But who gives a shit about it? It's just not very useful. The thing we really need to know is what does a 1 in 100 year daily precipitation event look like? And climate modelers are generally not used to generating that information because they're doing climate research. And then there's the whole issue around open access to the data. And what happens a lot now is just repackaging of climate data, and it's just not serving the needs of the market. We need to be able to do this sort of thing. We need to be able to combine climate data, sea level rise data, financial data, in this case house values, to diagnose climate risk. This is Waihi Beach, north of Tauranga. I apologize if this is one of your houses. 2 meters of sea level rise is everything covered by red. And you can go and see that there's just in this little spot that we just randomly picked, there's $24 million worth of house value at risk there from extreme sea level rise. Now, the ability to model that around New Zealand is currently largely lacking for various reasons. There is the STRAND project that's being funded by the Marsden Fund and run out of University of Otago that's making good progress with doing some of this work. But that's the interface between economists, finance, and climate, where there's a lot of innovation that can happen. Now look, New Zealand passed this law, and I'm sure you're all aware of it because I'm sure, like me, you read acts as they come through because they're so interesting. The Financial Sector Climate-Related Disclosures and Other Matters Amendment Act, it just rolls off the tongue, was passed a year and a half ago. And what it did is it looked at 200 financial institutions in New Zealand, each with at least $1 billion of assets in New Zealand, and made certain requirements of them under the Act for climate risk reporting. So reporting on physical climate risk. Imagine you're ANZ Bank, and imagine you've lent $17.9 billion to farmers in New Zealand, and imagine there's a risk of 2 extreme droughts in a row. What is the likelihood of farmers defaulting on those loan repayments in such a way that it destabilizes that whole loan portfolio held by ANZ Bank? And so that's a physical climate risk on that asset. Or if a company just has a lot of built infrastructure around New Zealand, what's the physical climate risk? There's also transition risk. If you are using a lot of coal to do something and you need to transition to using hydrogen or hydroelectric power, what's the risk that comes with that? There's liability risks. So there's a whole lot of reporting that needs to be done. That reporting is being defined by the External Reporting Board. And when I've asked about those 200 agencies, how prepared they are, do they have the tools to meet the needs that are being imposed on them by the External Reporting Board, the answer is hell no. They don't have the tools. New Zealand was one of the first countries, in fact, I think it was the first country to pass this sort of legislation. It came out of the Task Force on Climate-Related Financial Disclosures after the Paris Agreement. First country to pass this legislation. Many more countries have passed similar legislation. When I say many more, maybe a dozen, but there's a lot to come. There's an opportunity here for New Zealand to develop the tools that those 200 companies need to do their XRB reporting, but those tools are highly translatable to offshore markets. As that legislation comes in other countries, there's no reason why those CLIM, I'm sort of calling them climate finance tech tools, can't be applied globally. There's a huge market there. You think about it, 200 companies, $1 billion each, they're probably going to be paying about $500,000 a year per report. It's a $100 million market just in New Zealand. It'll be bigger offshore. The fifth thing on this list, and soon I'll tell you about how this list came to be, but there's the Green Finance Initiative, and under the Act, it encourages financial institutions to invest in low carbon and sustainable projects. And just to remind you that $300 million additional dollars went into the New Zealand Green Investment Finance Fund in this year's budget. There was already $400 million, about half of it is being committed. But when you go and look through the 17 projects that are being funded through the NZGIF, it's quite different to a typical venture capital loan portfolio or investment portfolio. There's a lot of room in New Zealand to be investing in these new technologies that connect climate and finance. And of course, rather than reading the whole act, I just got a ChatGPT to generate these bullets for me, of course. Speaking of ChatGPT and artificial intelligence, the interface between artificial intelligence and climate science, there's a lot of opportunity there. There's a whole group called Climate Change AI that is working to bring AI tools to climate science, in part because of this huge cost of running climate models. If you can train an AI system to learn the climate system, you can run climate models at a much lower cost. And I won't go into too much detail on that. We have a project funded through the MBIE Smart Ideas program called Deep Weather. It's using AI to improve the fidelity of weather forecasts. Through the Emergence Whakahura program, and I think Dave Frame will talk a little bit more about that. Dave leads this program. We've been doing things like using convolutional neural networks and artificial intelligence to figure out what do 1 in 100 year rainfall events look like in New Zealand. And that's this plot here, where we've done this at 1.5 kilometer resolution, which is only possible using AI in a way that it learns the spatial structure of extreme precipitation. And also how the severity of extreme precipitation events are expected to change in the future. This is a small little map that shows the percentage change in the severity of 1 in 100 year precipitation. So these are very unlikely events. They only happen once every 100 years, which begs the question, if you only have, let's say, 80 or 90 years of precipitation observations, records over the past, how do you figure out what a 1 in 100 year event looks like when you haven't seen any? And there's a whole lot of theory behind that, but the use of AI really helps in that regard. But this shows the percentage change in that 1 in 100 year event severity with a 1 degree C change in global warming. And you can see, for example, on the west coast of New Zealand, you could have maybe 10, 11, 12% change in extreme precipitation as the climate warms. And we've also done things. We've established a company recently called Red Sky AI that uses AI purely for weather forecasting. So it doesn't rely on numerical weather prediction models at all. But when you look at this intersection between weather and climate events, and especially extreme events, quantifying the vulnerability of communities to those extreme events, and the exposure of those communities, that's all about climate adaptation. There's so much opportunity for innovation in this space that can be developed and trialed and tested in New Zealand, but it's absolutely deployable in offshore markets because it's the same climate system globally and everyone's going to be facing these sorts of challenges. So there's plenty of opportunity to do cool stuff here. I think what we need is investment in people, the capital. NZGIF has that capital, and I think we just need to create opportunities for example, doesn't have to be just the New Zealand Green Investment Fund. I'm also thinking of Coin South, who's doing a great job in supporting startups. The ability for startups to get involved in the space is also great. So look, that's all I'm going to say for today. And I think we now have Dave Frame on the line. And let's see if Dave is there.
Can you hear me?
Kia ora, Dave. I can hear you. I think everyone else can too.
Great. Okay. All right. So I was really going to just talk a little bit about, can I share my screen, or would you want to run the PowerPoint? Okay. So
as always, Dave, I will do what you tell me.
Thanks. Okay. Thanks, Greg. So really, I wanted to talk a little bit more about the climate change mitigation side. If you go forward to the climate and strategy slide, so slide 2 should be a bunch of arrows. Yes, I can't unfortunately see your screen, so I'm having to rely on, so slide 2. So the basic point here is if you possibly push the button a couple of times, 1, 2, 3, 4 times. The basic point here is that what we're really trying to do in this is match our capabilities to our aspirations. Strategy is about the alignment of potentially unlimited aspirations with necessarily limited capabilities. One of the challenges with climate change is that people are sometimes sluggish about realizing what their capabilities are. So our climate mitigation potential, which ultimately is our capital, our labour and our natural resources, about harnessing that and realising what the opportunities are, we can be a little sluggish. At the same time, I think we have probably been a little optimistic in terms of the targets we've set. The world as a whole won't stay under 1.5 degrees. Our climate targets at the moment in New Zealand suggest that we're going to do everything we can. We're going to derive our carbon budgets from being consistent with 1.5 degrees. That will mean that we're working with negative carbon budgets within about 15 years. The world as a whole won't stay under 1.5 degrees. The main reason for that, we can show that pretty easily. To stay under 1.5 degrees, global CO2 emissions have to fall at about 9% per annum, compounding for 30 years. COVID knocked about 6% off 2020 emissions compared with 2019, which was an appreciable dip, the largest dip ever. But the idea that the world as a whole is going to have COVID and a half emissions reductions compounding for 30 years seems pretty fanciful. The world champs, as they like to remind us of emissions reductions, are the UK, who've reduced their emissions by about 3% per annum over the last 30 years. That's a good effort, but the world as a whole needs to go 3 times as fast as that, with around 1/3 of the income that the UK has. So if we can move on to the next slide. Climate change economics is normally, the 2 dimensions of it are mitigation, which refers to our efforts to reduce or prevent emissions of greenhouse gases. And this usually uses energy economy models to try and understand the impact of different policies on society, the economy and climate. And the other side is adaptation and impact. So adjusting to the kinds of changes we expect, and it uses a real range of tools, spatial information and so on, to try and, get a handle on what assets are at risk, and those assets, to use Treasury's breakdown, in natural, financial, cultural and social, and try and figure out how they're at risk, but also what the opportunities are and where they are. And that's a place where I feel like Southland is actually in a pretty good spot. because compared with a lot of the world, the sorts of changes you might expect to see are comparatively mild compared with many other parts of the world. So I actually think you'll have some opportunities in there as well, which is a good thing and not something everywhere can say. Next slide. Next slide again. I'll skip over that one. Next slide, because I'll talk about this as one big thing. So what I did was I looked through, in anticipation of talking to you today, I looked through the 418 pages of the Climate Change Commission's report. And one of the things and I also happened to be on a panel last week with Rod Carr, the chair of the Climate Change Commission. One of the things that jumped out at me that Rod comes back to time and again, and I think people within the climate bubble in Wellington do, is the returns on carbon, the revenue per tonne of carbon dioxide for different products and services that we create. And Rod, who was a former Vice-Chancellor, of course, points out that a full fee-paying student earns about $5,000 per tonne of carbon. Steel and aluminium production is somewhere in the 1,000s, and sheep and beef farming is about $400 per tonne of carbon. And if we go to the next slide. Oops. Yeah. And so, if we have a range of activities, and New Zealand's ones are kind of on the left, and I've just got some, potentially other sectors on the right. If you push the button, if you kind of imagine a carbon price, it's a little bit like the other sea level rise, really. So if you push the button again, as the carbon price rises, as people everywhere, push it again, as people everywhere start to kind of have prices or experience prices, or the demand for services, goods and services elsewhere expects a price and puts a tariff on you if you haven't got a price, then potentially some parts of our economy may end up becoming less favourable. Now, I'm actually an optimist about sheep and beef farming. Push the button again. Yep. And I think that if we design good policies, we don't have to sink under the waves at all. And I'll return to that point in a couple of minutes. I also went through the report and looked at the number of times Southland was mentioned in the report. And one of the things that comes out from a mitigation standpoint is that in general, these are drawn, these are paragraphs. You can see the numbers on the left from the big Climate Change Commission report. And many of these are challenges, I think, for Southland. They point out that hard to abate sectors are located in places like Southland. Regions that are reliant on primary industry, such as Southland, could be more exposed potentially to shocks in the weather, although I don't think you are, especially compared with some other parts of the country. Regional employment, where you have concentrated things like the smelter and the Glenbrook steel mill, which is an interesting case, which I'll come to in a second, where those kinds of things are geographically located. If you make a lumpy decision to move away from these sorts of industries, then of course you end up with these regionally concentrated economic shocks. And part of the just transition is trying to find a way so that particular communities don't bear a disproportionate burden of climate mitigation policy. And Southland has that in two ways. It has it through the smelter, but it also has it through being in a sector where sheep and beef farming is a big part of what you do and your identity. And it, as a sector, faces the same sorts of concentrated risk or exposure to policy, bad outcomes from policy that the geographically located places face as well. Now, of course, in the final one down here, in the initial report, they assumed that the smelter was going to close in 2027. In the recent material, they've walked back from that. But they still point out that potentially there are job losses on the line if that happens at some point. And I think really finding a low carbon future for skilled workers in Southland is something that really ought to be focusing the mind at the moment. And I know there's a lot going on in that space, which is terrific. So if you move forward one slide, there is a lot of talk about just transitions in Wellington, and it's a phrase you hear a lot of. Push the button again. But there are some mixed signals, and some of this is due to the customary framing of climate change. So push the button again. On the left we have aluminium. On the right we have steel. People, and one of the peculiarities is that people talk about low carbon aluminium, our fairly low carbon aluminium smelter, as though it's a problem. And as in terms of, well, we could take those electrons, those green electrons, and we could use them for other purposes. Whereas, on the other hand, a high-emitting plant like the Glenbrook Steel Mill, the government's just ploughed $300 million of either taxpayers' money or ETS revenues, depending on exactly how you want to see it, into a high-emitting steel plant to make it low-emitting. So why is the aluminium, that's always been quite low carbon, a problem, where we think we might use the electrons a different way, but the steel is worth subsidizing? So go forward one slide. And the answer is that this has a lot to do with the framing of climate policy. It has to do with when green investments were made. So the EU very strongly focused, and they tend to control the framing, and they tend to be very good at getting their messages out to NGOs, and NGOs play a strong role, certainly in New Zealand, in shaping the way the media express these points in public, which is a frustration of mine. The EU had very high baseline in 1990. They had very high emissions, which they tend not to like to talk about. But they had some early reductions. They had a bunch of reduction through the end of the Cold War, Thatcher closing the coal mines, German reunification, and the retirement of some very old, very poor plant in Eastern Europe. But what it does is it ignores the preceding context, and it ignores the fact that you're starting from a high level is bad for the climate in the first place, and starting from a low level, like having Manapori rather than the coal plant, is better for the climate. And this can create some odd behaviours and some odd incentives where you have a narrow focus on decarbonisation rather than sustainably using low carbon. So go forward one slide. And really what I think we need to do is use another lens. We need to actually use multiple lenses for thinking about this. And among the ways I would suggest doing it is to try and benchmark domestically our sectors and our firms and our regions, benchmark domestically against best global practice in terms of emissions, either per dollar earned or per kilogram of product produced, and have that as part of the conversation, as well as, you know, to round out the context so it's not just on emissions and reductions in emissions in a percent term. The basic point here is that this broad context, if you're the greenest, so I've chosen one sector here, which is kind of arbitrary. It's imagine New Zealand earns $4,000 per tonne, and imagine the Australians earn $5,000, then we ought to be looking to move up that value chain, as it were, in terms of the return on carbon, and try and become to be generating the same amount of revenue per tonne that the Aussies are using. But in some cases, we may have a lower emitting or a lower return on our carbon investment, but we actually may be the best in the world. And I think that's one of the gripes that the sheep and beef farmers have, is that we're actually incredibly efficient by global standards at producing those goods. They just happen to be lower than some of these other things like tertiary education. The world can't eat degrees. The world needs to eat food. And as long as we're good at that, that's a relevant consideration that ought to be part of our policy mix. And the way I would deal with that is by having part of our plan to be indexing against the best in class, against our competitors, against the international markets we're selling into, rather than, as part of a way of ensuring a just transition. It's not very just if we get out of something we're very good at and very efficient at, and the world as a whole ends up just simply emitting more while making the same amount of product, and all we've done is retire a bunch of jobs and get rid of some stuff that was pretty efficient. So that would be a bad outcome. So for a just transition to really occur, we need to be much more focused on a rounded picture of carbon efficiency, carbon competitiveness, international fairness, and horizontal equality. Last slide is the next one. The other dimension of this, of climate economics, which I haven't really talked about, Greg touched on, is that scientists and economists are working together. I direct this thing called Whakahura. It's extreme events and the emergence of climate change. We're trying to get a better understanding on the costs of extreme events, how those extreme events are likely to change in a changing climate, and how we might then go about thinking about the natural, cultural, financial, and social assets that are at risk, and how we might make them more resilient and potentially, get gains from doing that and exploit new opportunities. We're working with the Reserve Bank, Treasury, Ngāti Porou, and Ngāi Tahu through the Ngāi Tahu Research Centre here in Christchurch, and we're about 3.5 years through a 5-year project. And it's really New Zealand's main investment in this idea of in trying to understand the consequences of extreme events and climate change, and we're hoping to build on it into the future. That's all I'll say. Thanks very much for having me along.
Thank you, David, for that. I hope you can still hear us. We appreciate it very much. Our final speaker in the session is Lee Chambers. He might just run slightly over time. I don't want him to, he's got the crumbs of the session. I want him to take as much as he needs to do what he needs to do. We appreciate him being here. So Lee has a PhD in hydrogeology from Lancaster University, and he's a groundwater modeller at GNS. And according to Mike Shatford, Lee's favourite 1980s band is Wet, Wet, Wet. Oh, you said that joke would work, it worked.
Hi everyone, the lunchtime snooze slot. I'm here to talk about rising groundwater levels as a function of sea level rise. Just a little bit about myself. I'm actually an environmental scientist with a specialisation in groundwater science, and before arriving in New Zealand I worked quite heavily in groundwater resource projects in sub-Saharan Africa, principally in Malawi and Mozambique, and now I'm arguably masquerading as a groundwater modeller at GNS Science. I just wanted to make an apology. Firstly, I've got a lot of ground to cover in a short space of time, so please give me a shout after the session if you have any questions about anything that I've said, or if you're interested, just for a general chat. So start off quite simple. So what is groundwater? Groundwater is any form of water below the Earth's surface. That could be saline groundwater commingled with oil and gas deposits several kilometres below the Earth's surface, or typically what we're more interested in is fresh groundwater less than a few hundred metres below the Earth's surface that's of sufficient quality and quantity. So groundwater's a hidden asset, and that's particularly the case in New Zealand, where it's estimated that 80% of annual river flow comes from groundwater. It's critical for sustaining surface aquatic ecosystems. Approximately 40% of New Zealanders depend on groundwater for drinking. Irrigation from groundwater contributes an estimated $2 billion a year to the economy, and groundwater may be more resilient than surface water during times of drought. But on the one hand, groundwater might be more resilient, but on the other hand, there are several threats to groundwater, and I've broadly categorised these into 3 spheres of influence, and that's threats from human activities, climate change, and natural climate variability. But obviously, I'm here today to talk about rising sea levels and rising groundwater levels. Just as a quick aside, if we think about nitrogen-based fertiliser application, even if we would stop applying nitrogen-based fertiliser today, you would probably see increases in nitrate levels in groundwater systems for decades to come, and that's because of the range of travel times in a typical aquifer system, anything from a few years to several thousand years. So, if we stop today, you've got nitrogen stored in the unsaturated zone, a wide range of groundwater travel times. Essentially, these systems are really slow to respond, and it's a roundabout way of saying that if any policy actions we take today may take years to measure, just because how slow these systems respond. I move on. So at GNS Science at the national scale, we have a national model of groundwater flow. We typically use this national model to inform local models or identify areas that are more susceptible to sea level rise and climate change. I don't really have time to discuss this slide in any great detail, just more to emphasize the point that when we build numerical models, we design these models to answer specific questions, and the model I'll present a case study from South Dunedin today that's looking at groundwater flooding as a function of sea level rise. And on the topic of sea level rise, as part of the MB Endeavour Sea Rise programme over the past 5 years with collaborators, GNS Science developed updated sea level rise projections for every 2 kilometres of New Zealand's coastline. And here's a kind of an infographic just to show us zooming in on sea level rise projections for Southland. And if we think about vertical land movement, there are some parts of Southland that are rising and sinking. If you think about sea level rise and subsidence, that would compound the effects of sea level rise. And just want to draw your attention to the fact that even if we stopped emitting fossil fuels today, which is not going to happen, we're still going to get around about 30 centimetres of sea level rise. And also just draw your attention to the fact that there's a huge uncertainty post-2050 in the sea level rise projections, but really up until about 2050, 2060s, it's looking fairly certain that we're going to get around about 20, 30 centimetres of sea level rise, and I would argue that we're going to get some pretty severe consequences due to sea level rise. And this is an infographic borrowed from Greg. Thank you, Greg. Just to get us thinking about what might happen at the coastal margin as sea level rise and groundwater levels rise for hydraulically connected systems. So as you might imagine, so this is an infographic showing groundwater levels in relation to ground level. So as sea level rise, groundwater levels rise, that might compound the effects of surface inundation from surface water. It might compound the effects of 1 in 10-year, 1 in 5-year precipitation events. And sort of 2040, 2050, you might start to see health issues, insurability of housing might become an issue. And as we move forward, you might start to see stranded assets, loss of crops, remobilisation of contaminants. And this is all before groundwater emerges at the Earth's surface. So I'm not trying to scare everyone, but just to get us all thinking about, what might happen with sea level rise at the coastal margin. And also, I'd like us to think about what might happen if we had a Cyclone Gabrielle type event in, say, 2050, or 2100. It's important to think about the fact that, if groundwater levels are already high and we have a cyclone type event at the coastal margin, this really could have serious consequences on surface flooding. I won't go any further into that. And this is just, again, the New Zealand Sea Rise project. There's a lot going on in this slide, and I don't really have time to discuss it in any great detail. Just to say that the modelling we do at GNS Science, we embrace uncertainty. We embrace uncertainty in the sea level rise projections, uncertainty in the groundwater flow model, and this model of South Dunedin is predicting the probability of groundwater inundation as a function of sea level rise for different IPCC sea level rise projections, and we've actually developed a graphical user interface. This video should play now, which basically, the middle image is the probability of groundwater flooding for SSP3, and we can click on an area of South Dunedin, look at groundwater level rise as a function of sea level rise. That's the bottom right image. The top right image is the probability of groundwater levels in relation to the ground surface. And obviously, as I've just said, the middle image is a spatial map of the probability of groundwater flooding. And we're just going through an IPCC projection to 2100. But as I said, flooding will become an issue. Groundwater level rise will become an issue before groundwater reaches the Earth's surface, and we can just chop off 25 centimetres from the ground surface and look at the probability of, say, groundwater levels being 25 centimetres below the surface. And the reason we've developed this graphical user interface is just to allow the general public, decision makers, practitioners to interrogate the model and the model output. So this is looking at the transient progression of steady state annual groundwater levels over a 100-year period. And I would also argue that me personally and a few of my colleagues would like to move away from producing hefty reports that are thousands of pages long, where 900 of the pages are just, graphs of model outputs, where we could essentially invest more time on a web-based application where you can actually interrogate the model yourselves. That's something that I would prefer, and it's also easy to communicate with the general public, I feel. And And last slide, this is just to point everyone to aerial electromagnetic techniques that we have, SkyTem. So I've just labelled this slide, how do we see our groundwater systems? Think of an MRI scan for the body. We can essentially measure the conductivity of the subsurface, and this allows us to identify areas where an aquifer system might be, or clays that might protect a groundwater resource. And the huge advantage of these techniques is that they have huge aerial coverage, non-invasive. There's a huge improvement of just having a few boreholes and interpolating between boreholes. And I've just given you an example image at the bottom right of the conductivity of the subsurface. So low conductivity might indicate where an aquifer might be, and high might be an area of clays. Yeah, and just to point to the fact that we have access to these techniques that can really, reduce uncertainty in the subsurface. And just linking back to the start of my talk, just to kind of say why we do what we do at GNS Science is, obviously we're interested in safeguarding our annual river base flows due to groundwater, protect groundwater-dependent ecosystems. We want to obviously sustain New Zealand's groundwater-dependent freshwater supply. As I've just said, reduce uncertainty in our groundwater model predictions and protect New Zealand's economy and improve resilience to climate change, for example, during droughts. And here's just a few publications that we've put out recently, and obviously any questions, then please shout up. And that's me.